Hello, in this lecture we're going to talk about VSEPR theory, which is valence shell electron pair repulsion. This is an attempt to explain why we get 3D shapes in structures. You know, the bonding electrons and the lone pairs will repel because bonds are made by two electrons. Lone pairs, non-bonded electrons, are made of electrons. Electrons are negatively charged. Like charges will repel. We will end up with molecular geometry and electronic geometry. Molecular geometry describes the position of atoms in a molecule relative to one another. You may use ball and sticks model to visualize it. In this case, what I have here is methane. Lewis would have thought that we would stop at this point, and this implies that the molecule is actually sitting flat on your screen. That was wrong. The bonds are made of electrons, so we will have two hydrogens on the plane. So those two bonds are on plane, and then you will have one hydrogen away from you behind your screen, and then one popping out of your screen towards your face. So this is a representation of a 3D structure of CH4, what we call methane. And the reason why it's not flat but tetrahedral or 3D is because the electrons will repel. According to valence shell electron pair repulsion theory, the electrons making the bond will spread as much as they can in space. You can see that this is towards me and this is away, and these two are roughly on the plane. Now if you look at H2O has two lone pairs on oxygen and two pair of electrons that are in the bonds. The electrons in the lone pair will occupy more volume. These guys will occupy much volume in space than the electrons in the bonds. So they will repel the electrons in the bonds downwards. So if you are to discuss molecular geometry, which is a connection of elements, you're going to get an inverted V shape. So the molecular geometry of water is bent. So you get bent molecular geometry. In electronic geometry though, we consider the electron domains. Okay, each lone pair is an electron domain. A single bond is an electron domain. A double bond is one electron domain. A triple bond is one electron domain. So around this oxygen, we have 4 electron domains. And for that reason, the molecule is going to be said to be said to have an electronic geometry that is tetrahedral. And by the way, for hybridization's sake, when we have 4 electron domains, we basically by shortcut say it's SPPP, and that is sp3. The hybridization of the oxygen is sp3. That's the general idea what we're going to talk about. By the way, whenever you have an electron on the central atom, the electronic geometry, like here water molecular geometry is bent, the electronic geometry is different from the molecular geometry when you have a lone pair on the central atom. So water has a bent molecular geometry but tetrahedral electronic geometry. Alright, so electronic geometry is the arrangement of bonding and unbonding electron pairs around the said central atom, or the atom in focus. So hybridization is a mix up of the orbitals SPD. Those are the most common. So you're gonna end up with, say, sp if you combine s plus p, or you end up with sp2 if you combine s plus p, or you end up with sp3, which is spp, or sp3d if what you combine was s, 3p's, and a D. So we would call those sp, sp2, sp3, sp3d. Now this is going to be taken to be 4 electron domains. Okay, this will be taken as 3 electron domains. sp2 is taken as 3 electron domains, and sp is going to be taken as 2 electron domains. This is a shortcut we want to use to describe what we see in the table. So let's say that you have CO2. Let's say that you have CO2, carbon 4 oxide. How many electrons domain do we have on that carbon? One electron domain could be a single bond, could be one double bond, could be a triple bond, or a lone pair. So this carbon in the middle has 2 electron domains, a double bond to the left, a double bond to the right. So we predict that the hybridization will be sp, because orbitals are areas or locations around the nucleus where you are likely to see an electron. We call that location a domain or a region. So if we have 2 electron domains, we can quickly predict that the hybridization will be sp, and for electrons to be further away from each other, according to VSEPR theory, electrons will repel maximally at a bond angle of 180 degrees. Okay, and then for trigonal planar, something like formaldehyde is gonna take a bond angle of 120 all around roughly, and not having 90. You will not have 90 because the electrons will repel as much as they can to maximize the space around them. Now you have the central atom that has 2 single bonds and a double bond, so that is 3 electron domains. So we predict spp, which is sp2. Bond angle for sp2 is usually roughly 120. And then tetrahedral, will take an example of methane. You know, the carbon right there has 4 electron domains, which is 4 single bonds. So you have 4 electron domains. If you have 4 electron domains, you are predicting the hybridization to be a spp. The bond angle of sp3 hybrid orbital is roughly 109.5. This can change if you have lone pairs. Can reduce to 107 or 104. You'll see that later. Trigonal bipyramidal is showcased by, for example, phosphorus pentachloride. That P right there has 5 electron domains. Okay, 5 electronic regions or groups. Groups, domains, regions, same thing. So we expect that we'll have SPPP. The P subshell will have 3 p orbitals, and then we'll have a D to make it 5 electron domains. And then there's also octahedral, which will take you to D2, and the bond angle for that will be a mixture, will be 90. For trigonal bipyramidal will be a mixture. We'll talk about that. So if you look at CO2, which is a classic example of a molecule that has linear molecular and electronic geometry. For molecular geometry, we are connecting the elements. It's a straight line. The electrons, according to VSEPR theory, will repel themselves maximally in space. The bond angle will be 180. The central atom does not have a lone pair, so I expect molecular shape to be equal to electronic shape or geometry, and the bond angle should be 180. As far as hybridization goes, since I have 2 electron domains, 2 double bonds giving me 2 electron domains, okay, so I have 2 electron domains. Since I have 2 electron domains, the hybridization of that carbon is expected to just be sp. For trigonal planar, I'll use formaldehyde. Like I said, you don't expect 90 degrees because we do have lots of space on this side, suggesting 180. So instead of having 90, 90, and 180, the bonds will spread equally all around according to VSEPR theory. The bonds will repel. Bond angle will be 120. Now for molecular geometry, which is just connection of the elements, connect hydrogen to oxygen, you get a triangle. And they're connected even in there. So the molecular geometry is trigonal and planar. There's no lone pair in the central atom, so the molecular geometry is predicted to be similar to the electronic geometry. It will be trigonal planar. As far as hybridization goes, for the elements, I'll show you that the carbon right here, hybridization will be predicted based on the electronic geometry and electron domains. So we say that you have a double bond, a single bond, a single bond. So there's a 2 single bonds and a double bond. So we have 3 electron domains. And because we have 3 electron domains, this is predicted to be spp or sp2. The bond angle for sp2 again is roughly, to repeat myself, 120. It's gonna be roughly 120. This is the oxygen up here, and you see from this model the bonds are quite spread maximally. This nose, if you are to count the electron domains, you're counting these guys, the double bond, single bond, double bond. Again, you're making a triangle that's trigonal and planar. For tetrahedral, again, the hydrogen will be away. This will be toward you in 3D on the plane. For molecular geometry, you're connecting the elements. Now you know the story, you know the drill. Connect the elements, you're going to end up molecular geometry being tetrahedral shape, Mg. And then do we have a central lone pair? No. The electronic geometry is also gonna be tetrahedral. As far as hybridization goes, the carbon in the middle has 4 electron domains around it. This carbon has 4 electron domains around it. So if we have 4 electron domains, we expect again sp3, and therefore the bond angle is going to be predicted to be roughly 109.5. There's no lone pair on the central atom. So molecular geometry is going to be the same as electronic geometry. Ammonia will have 1 hydrogen away, 1 toward us, and then 1 on the plane as a screen. You also have a lone pair. Okay, so I'm going to draw the 2 of them so we can explain both Mg and Eg. So for molecular geometry, again, my concern is just the elements to be connected. I end up with this shape. That's of a pyramid, and each side has 3 corners. So we'll call molecular geometry trigonal because of the triangle on each face, but it's the shape of a pyramid, so pyramidal. However, the central element has a lone pair. The central element in question has a lone pair. So the molecular geometry, molecular shape, is going to be different from the electronic shape. For electronic shape, we count the electron groups, electron domains, which is this list. So I see that I have 4 electron domains, and because I have 4 electron domains, I quickly predict SPPP, which translates to sp3. Now you would have expected that the bond angle between 2 groups, this is the lone pair, by the way, that's a lone pair. You would have expected that the bond angle between 2 groups to be 109.5, the standard one, but it's not 109.5 because there's a lone pair. The lone pair occupies much room. These bonds are repelled downwards. The bond is going to reduce by about 2 degrees to about 107. according to valence shell electron pair repulsion theory. Okay, but that's how you predict the bond angle, electronic shape, molecular shape, and hybridization. Okay, let's look at water. When you have H2O, it has two lone pairs in the Lewis structure. So molecular geometry, I'm just connecting the element. That's an inverted V alphabet. So we call that shape bent for molecular shape, molecular geometry. Now, because we at least have one lone pair on that oxygen, the electronic geometry will be different, and we are going to count the electron groups. Let me draw the molecule here. How many electron groups do we have on that oxygen? Usually in the test you'll be asked for which element, so you'll know which element you're focusing on. An electron group, an electron domain is a lone pair, so I have 1, 2, and then I have these two here. I have 4 electron domains. Anytime I have 4 electron domains, I'm thinking sp-p-p, which translates to sp3 hybridization on that oxygen. And in that case, one would have thought that the bond angle is 109.5 degrees around the bonds, but that's not true, because again I'll have you remember that the lone pairs on the water molecule, on the oxygen in the middle, they would occupy much volume, repelling those hydrogens downwards and even compressed towards each other, and the bond angle even reduces further to about 105 or 104. In ammonia it was 107. In CH4 was 109.5. There was no lone pair in CH4. The moment you have a lone pair, then you get reduction of bond angle between the two bonds. Again, all that is because of the valence shell electron pair repulsion theory. The electrons repel in space. Okay, and then lastly, I'll show you an example of trigonal bipyramidal using PCl5 as an example. There's no lone pair in the central element, but again, if you connect the elements on top, you're going to have a pyramid, and so will you have it at the bottom. Okay, so you have a pyramid on top and a pyramid at the bottom. So the molecular shape is, you see how you have each side, each face has 3 things, 3 corners. So you get trigonal by 2 pyramids, bipyramidal for Mg. Now, because there's no central lone pair on the central atom, that's gonna be the same shape for electronic geometry. As far as hybridization goes, you do have 5 electron domains around that said phosphorus. So if it's 5 electron domains, I expect S, P, P, P. I've exhausted my 3 P's in the P subshell. I'll add a D. So the hybridization in this case will be D, sp3, or you can write it as sp3d. Bond angle is varied. You have a 90 here, but you have a 90 on the plane in the middle. We have a 120 on the plane in the middle. So you have both 90 degrees and 120, because right in the middle here it looks like a triangle. So the bond angle is 120, and then up and down is roughly 90. And that's how you predict molecular shapes, electron shapes, electronic shapes, hybridization, and bond angles. If you apply this method in whichever molecule, you get it right. Bye. See you for another lecture next time.